Okay, so before we start all this, some reminders. So what's due Sunday is the Chapter 3D questions. So we're going to finish up Chapter 3D either today or Friday. If we finish it today, Friday's going to be a review day. Y'all are welcome to come. Otherwise, I'll post the video from it. The discussion is also due on 3D by Sunday at midnight as well. So we have an exam coming up since we're finishing a chapter. This next exam is on chapters 2 and 3. So it's a larger amount of material than chapter 1. So it's going to be due Wednesday, October 7th at midnight. I will have it up Sunday. So if you are feeling confident, you have the information you need, you can take it on Sunday if the weekend works better for you. But it will be up and available through Wednesday at midnight. I have a review sheet as well as a practice exam ready. I want to go through them one more time before I post them. So they're all ready. I'll be posting it sometime today. Okay, so I'd like to get that up a week in advance so you have time in case you want to do and take it on Sunday. All right, so that's it for that. Questions on what's due? Anything like that? Okay. So we'll get into this molecular shapes. So we've been learning how to draw Lewis structures. So we've been counting valence electrons and then using those valence electrons, figuring out what the central atom is, and basically making everybody have an octet, making everybody happy to come up with a Lewis structure. So these are the Lewis structures that we've done in the previous classes. So I just redrew them. So if you don't remember how to draw them, how to come up with the Lewis structures that you're seeing here, look back at the previous videos because we went through them in detail, step by step, on how to make them. What I want to focus on today is the next step. So once we have the Lewis structure, what do we use that for? And we use the Lewis structure to come up with the shape, the 3D shape of the molecule itself. So we do this through the VSEPR theory. So what VSEPR stands for is valence shell electron pair repulsion. Okay, what that means is the valence electrons help define the shape. Because remember, valence electrons are the electrons that are involved in bonding, those outer shell electrons. So we're going to use those valence shell electrons to help us figure out what this is going to look like in 3D. Okay, so we're going to use our molecular shapes and VSEPR packet to figure out these shapes. And you guys have it good because in the past you didn't get this on an exam. You would have to memorize these shapes and you actually get the packet. So, because you're taking it at home, it's an at-home test. So we just need to know how to use this, right? Because you don't want to get to the test and then try to figure out how to use this packet. So that's our goal today. So we're going to start from the Lewis structure itself. You'll see on the first page of this packet it says 6 steps in drawing the shape. The very first step, draw the Lewis structure. Okay, so that's what we've been focusing on the last 2 class periods, is how to draw those Lewis structures. So the second step says count the things around the central atom. So when we're figuring out the shape of a molecule, we're only looking at the central atom. Okay, we're not worried about the terminal atoms. The terminal atoms count as things, but they're not going to define the shape itself. So what do I mean by that? So when I say count things around the central atom, a lone pair, so remember 2 dots like we have on this nitrogen atom here, that counts as just one thing. I know there's 2 electrons there, but the pair itself is one thing. What else counts as a thing? Atoms. So for example, in this first one here, we have carbon dioxide, right? Carbon with 2 oxygens. So if I were going to count the things around the central atom's carbon. How many things? Does it have any lone pairs on carbon? No. How many atoms are around carbon? Just 2. Okay, it doesn't matter that there's double bonds. It wouldn't matter if it was a triple bond. We're looking at how many atoms. Okay? So there are 2 atoms around carbon. So what I'm going to do is I'm going to turn, and I numbered these to try to make our life easier, to note page 4. Do you need one of these packets?
I do.
You have it. So we're turning to page 4, and notice it has number of things, comma, number of lone pairs. So that first number present is the number of things. So we have two choices since we have two things around the central atom. The first choice says 2, 0. And what this means is there's two things around the central atom, and 0 of those things are lone pairs. So this is the shape we have because we have two things, but both of them are atoms. 0 of them are lone pairs. So we follow this over, and we see the shape is linear. And then it also gives us the bond angle as we follow it over. 180. And we're actually doing a lab where you're going to be going through all of these steps. You're going to be drawing the Lewis structure, you're going to be writing the shape, and then you're actually going to be drawing the shape. So if I drew the shape of this, since it's linear, it's going to look pretty much the same. The only difference when you draw the shape is you don't include the lone pairs on the terminal atoms. Okay. In the picture you see, it's a ball and stick model, but you don't want to do this as the shape, because if you know the elements, put the elements in for those dots. Okay, so this is just trying to show you the shape. You need to fill in the elements yourself. Once we get into some 3D shapes, because this is all linear in the plane of the board, it'll get a little more detailed in the actual drawing of the shape itself. Are there questions on that first one? Okay, so for the next one, so if we're trying to figure out the shape, the 3D shape, how it looks in nature, we start with the Lewis structure. We drew this last time. We're going to count the things around the central atom. So the central atom is nitrogen. So how many total things around it? 4. So the atoms each count as 1. So we have, let me actually just count. So we have 1, 2, 3 things. And the lone pair counts as just one thing. Even though there's 2 electrons there, that whole thing just counts as 1. So there's a total of 4 things around it. So then we look, we're still on page 4, we'll find where it has the 4s. And there's 4 different choices. There's a 4, 0, 4, 1, so on and so forth. So we have 4 total things. Now after the comma, what goes here, this next number is how many of those things are lone pairs? Just 1. So we're looking at the 4, 1. That's going to give us the shape of this molecule. So it's saying that it's trigonal pyramidal.
Oh, so you don't want us to draw the shape, just label it?
You need to draw the shape too, but I'm starting just with the name. So we'll draw it down here. That's why I left some extra space. Because when you get to lab and then also on the exam, sometimes you're going to have to pick the shape itself, like the 3D shape, what it looks like. Sometimes you're going to have to pick the name of the shape. Sometimes you're going to have to pick the bond angle. So if I followed over, we have the shape, and the bond angle is less than 1.5. So this is not the 3D shape. So if I wanted to draw it 3D, what I would have to do is I'm going to follow kind of what they did here. Nitrogen's in the middle, I have a hydrogen going down, and then I have these wedges and dashes. So I'm going to talk about the wedges and dashes a little bit. I'll show you next week again. So this wedge, what that's meaning is that that hydrogen is coming out of the plane of the board. Okay, so it's coming out at us. So this is the board, it's coming out like this. The dash means it's going into the plane of the board. So it's going to be like this. So if you look at the tripod that I have the camera on, that's pretty much the shape without the camera. One of the legs is one hydrogen, the other 2 legs are the other 2 hydrogens. So I don't have my ball and stick model, but I got my tripod to show at least the people in class what that looks like in 3D. And the lab that we're doing on this actually, we're building the models in 3D with balls and sticks, so you'll be able to see these molecules if you come in person to lab at least. All right, questions on this one? Now this part you're not gonna have to know. You're not gonna have to write 4,1 or 2,0 for a test or something. I'm using this to try to show you where you're looking for the answers. Okay? All right. So let's try the next one. What's the central atom? Carbon. How many things does it have around it?
2.
So that's tricky, right? Like you see a single bond and then a triple bond, but the bonds themselves don't matter for the things. You're looking at the atoms, and it just has 2 atoms, a hydrogen and a nitrogen. So we have 2 things. So we're looking at 2, comma. So out of those 2 things, how many are lone pairs? 0. They're both atoms, right? 1 atom, 2 atom, no lone pair. So 2, 0 is going to help you find the shape, the angle, all that good information. So the shape is linear. It's just like the carbon dioxide one. And then that makes the bond angle 180. All right. So I know that one was similar to this, but I just wanted to show it doesn't matter what type of bond. It matters how many atoms. So let's try one that's a little different now. To draw the shape of it, it's going to look pretty much exactly the same. You just don't include the lone pair on the terminal atom. And the only time you're going to have to draw these yourself are during lab. Otherwise, it's going to be multiple choice, and you just need to pick the correct one. So, all right. Try a harder one. Let's look at carbon, and there's tetrachloride. So carbon tetrachloride, which one is the central atom? Carbon, okay, how many things around it? 4, so 4 chlorines, so 4 comma. How many of those things are lone pairs? 0, right? You're just looking at carbon. There's lone pairs in the chlorines, but we're not worried about the chlorines, they're terminal, we're worried just about carbon. So there's no lone pairs on carbon. So 4, 0. So what shape is this guy going to be? Tetrahedral. Yes, so we're the shape up here, tetrahedral. And the bond angles are 109.5. So I'm just following that over to get all that information, 4, 0. And the shape, it's going to be a 3D shape again. We have carbon in the middle. And we have our wedges and our dashes. It looks something like that. So I want to point something out. So notice over here, we have carbon with 4 chlorines around it. So now this looks like my camera on tripod with the camera on top. Okay, so this is a 3D shape. We got the chlorine atom with the wedge coming out of the plane of the board, the chlorine atom that's dashed going into the plane of the board. And notice it's very similar to our nitrogen trihydride molecule. The difference is we took away this chlorine and replaced it with a lone pair. And we don't draw the lone pairs in the shape. Okay, so it's the same shape without that top chlorine. Since we went and took away an atom and replaced it with a lone pair, it changed the bond angle slightly. So we have a 109.5 over here when it's all atoms. But when you change and add a lone pair, we get a less than. So the reason for this is the lone pair, it takes up more space than an atom does, than a single bond does. So since it's taking up more space, it's pushing those hydrogens down, causing that angle to be less than if there was an atom there. All right, tickle my jaw. Stop me if there's any questions. This is what we're going to do. We're going to keep going through these, and then we'll apply something else. So we did, let's do an ion. We can do ions. We did one of those last time, didn't we? Carbon. Now I got to remember what it is without counting all the valence electrons, and that would help. So people might need to look at their notes. I think it's a double bond here. Is that the correct Lewis structure? Or do I have to count the valence electrons to make sure? Does anyone have their notes from last time? Oops, forgot these guys. He wants to be happy too. Yeah, I think that's correct. Okay. It doesn't matter where the double bond is, it could have been here or here.
Yeah.
But they're all residence structures. So if we wanted to do this one, we do it the same. It doesn't matter that it's an ion. It doesn't matter that it has a charge. Okay, we're just using the Lewis structure to figure out the shape and the bond angle. So, how many things around the central atom? 3. So just looking at carbon, how many of those things are lone pairs?
0.
0. Okay, so now we're looking at the 3, 0. And this shape says it's trigonal planar. So what that means is it's all in the plane of the board. We don't have any dashes and wedges. So all of these atoms are in the same plane. It's a flat molecule. Okay, so if we draw this, it's just going to look slightly different. Because you know here we kind of have it in a T shape. For trigonal planar, we want it to look in a triangle shape. So you would just do that. And just kind of change in where they are slightly. Try to make it look like a triangle. And the angles on this are going to be 120 because if you think of a circle is 360, right? So if we take that circle that's 360 degrees and we divide it by 3, we get 120, and that's what these bond angles are right here. 120, 120, and 120. Questions so far? Keep going, put some more examples. That one, I'll write a bit more. So, we didn't get that one. Let's do this guy last time, 5. PF5. I didn't put all the electrons around it, but each of these had 6. So it kind of gets a lot. So this one was an exception to the rule, to the octet rule, because phosphorus has more than 8. It can, because it can get that expanded octet. Talked about that last class. So now let's take this guy and let's figure out what his shape should be. So now we'd have to look all the way over at page 5, because how many things are around phosphorus? 1, 2, 5 you said? And then 0? You say 0, because 0 of those things are lone pairs. So 5, 0 gives me that trigonal bipyramidal, or that guy. So to draw its shape, we are going to have to do dashes and wedges, because what we have is these 3 fluorines are going to be in the same plane. And then this guy is going to be a wedge, and that guy back there is going to be a dash. Okay. What are the bond angles? 90 and 120. There's 2 different bond angles. Because if you look at these 3 fluorines here, they're pretty much in a triangle, like what we saw here. So if you took these 3 fluorines and kind of looked at them from above, it would look like this in a triangle. So those angles are 120. It's this angle here that's 90. Because fluorine, phosphorus, fluorine. So mostly they're going to stick with 4 things or less. That's where you want to focus your attention on when you're studying. Okay. A lot of times with the 5 or more things, these are exceptions to the rule, right? It's going to be expanded octets, so you're not going to see a lot of examples with the 5 or more things. Okay? All right. Well, let's do one more. We didn't do this one yet, but he's going to be good to know for what I talk about next. So we'll do the whole thing. We need to do the Lewis structure. We've never done the Lewis structure of this guy, so let's do it. Because you're going to see him a lot. Water. Okay, so if I wanted to do the Lewis structure of water, so we're starting from scratch, we're going to get the Lewis structure, and then we'll go through all these steps, the shape and everything. Okay, so when we start, we have to figure out from the chemical formula itself which atom is central. Usually it's the first atom present. Do you think hydrogen's going to be central?
No.
No, it's always terminal, always. It can only have one single bond, that's it. So by default, it's got to be oxygen. So if I have oxygen, and then I'll put the two hydrogens, one on either side. So let's count our valence electrons next. When we do that, remember it's the number of atoms, which we get from the formula, times the valence electrons, which we get from where the elements are on the periodic table. So I like to make a list of the atoms present and then go from there. So how many hydrogen atoms according to the formula? 2. How many valence electrons of hydrogen according to where it is? 1. It's in group 1, so it's going to have 1 valence electron. How about oxygen's how many atoms? 1. If there's no number after it, we assume it's a 1.
6.
And then 6 valence electrons because it's in group 16. So then we add for our total, we get 8. All right, so for this guy, we need to make everybody happy. We start with the terminal atoms first. Are our hydrogens happy?
Yes.
Yes, so most elements want 8. Hydrogens are the exception, they only want 2. This single bond is worth 2. So that hydrogen has 2 electrons, that hydrogen has 2 electrons, because the single bond is 2 electrons. So how many does oxygen have? Because now we worry about the central atom.
4.
Well, he donates 6 to the cause, but he has 4 in this structure that we've drawn. 2 for this single bond and 2 for that, so 2 and 4. So he needs how many more?
4.
4 total. So 2, 4, we got to see how many we've used, right? We've used 4. And we have how many left? 4, and we just said that's how many he needs. Right? So if he needs 4, we add them as lone pairs. Because now we have 2, 4, 6, 8. So oxygen has 8 total electrons, a full outer shell, a full octet, happy. Okay, so this is how we come up with the Lewis structure. But from there, we can use how many things are around the central atom to figure out the shape. So how many total things around oxygen? 4. This is a tricky one because we have an atom as 1, this atom is 2, and a lone pair counts as 1 thing, so that would be 3. And this lone pair counts as 1 thing, so that would be 4. 4 total things, and then what comes after the comma is how many of those things are lone pairs? 2. We have that lone pair and that lone pair. So it's a 4, 2. So to figure out that shape, looking on page 4, 4, 2 says it's going to be bent. And the bond angles are going to be less than 109.5. Okay, so it would look like oxygen, a hydrogen there and a hydrogen there. We just want it to look bent rather than straight across. Because this, it looks linear. We don't want it to look linear when we're drawing the shape. We got to make sure it looks bent. Just like you're just following what they drew here. They drew it sideways. You can draw it sideways if you want. I always draw it that way. It's your choice. All right, so why are we learning the shapes? We're going to get into next. Are you guys feeling comfortable with finding the shapes from the Lewis structure? Okay, then I'm going to move on to why we're doing it. Because it's going to help us figure out some properties. It's going to help us figure out solubility. It's going to help us figure out melting points. And it's going to do that because we're going to use it to figure out if these molecules themselves are polar or not. So we've already looked at bonds, individual bonds. So if I wanted to figure out if this oxygen-hydrogen bond was polar, I used my electronegativity tables, I subtracted them, and then found what range they fell in, okay? But now what we're gonna do is look at the whole molecule, not just the bond. So, to figure this out, there's two ways. One is a list, and this list is included in the PowerPoints, but I'm gonna write it here. So for nonpolar, do no lone pair, and terminal atoms are the same. Carbon and hydrogen only, and diatomic. Oh, I just mentioned that because I wanted to talk about that last time. And then for polar, so these are just rules to figure out if a molecule as a whole, I should write molecule, is polar or nonpolar. So not just the bond itself, but the whole molecule. For polar, we're looking at one or more lone pairs. That's a LP is lone pairs. And then no lone pair. Not the same. Okay, so step by step, let's figure out how to tell if molecules are polar or nonpolar. So, let's use this water molecule as an example. Let's figure out if it's nonpolar or polar based off of these rules. So notice with the rules, we're looking at the Lewis structure. Okay? The reason we're looking at the Lewis structure is because the Lewis structure includes lone pairs in it. And we're also looking at the central atom only. We're not looking at the terminal atoms. So with this water molecule, looking at the Lewis structure, what category does it fall under? Does it have lone pairs on the central atom? Yes, it does. So notice it's going to fall over here. It has one or more lone pair. And I should write on central. Because that's what we're looking at, is the central atom, not the terminal. Okay? If the terminal atoms have lone pairs on them, who cares? That's not going to affect our polarity of the molecule as a whole. Because the molecule as a whole is affected by what's around it. What's around the central atom. Okay, so this is going to be polar due to that rule. The other way to figure out if it's polar or not, I prefer these rules, but some people prefer this other way, so I do want to show you. The other way is by a dipole moment. So to figure out dipole, you need to use the shape, not the Lewis structure. So these rules apply to Lewis structures. The dipole moment that I'm about to show you, you need to know the shape. So I guess part of the reason I like the rules better is because I can stop here at the Lewis structure and I don't have to go through and find the shape to continue on. So with the dipole moment, what that means is you need to figure out which atom is more electronegative, and then you're going to draw vectors or arrows towards the most electronegative atom. So it sounds a little confusing. What do I mean by that? So you're looking at individual bonds between the central atom and the terminal atoms. So if I'm isolating this hydrogen-oxygen bond here, I'm going to look and see, okay, what's more electronegative, hydrogen or oxygen? I'm pretty sure it's oxygen. So I would draw an arrow representing a vector pointing from the hydrogen to the oxygen. Okay, I need to do that to all atoms around the central atom. Not lone pairs, just to the atoms. Okay, so now I have this hydrogen. I'm going to do the same thing, because if I isolate this bond, the oxygen is more electronegative, so I would draw an arrow pointing there. So now I need to figure out if it has a dipole. What that means is I'm going to add the vectors head to tail and see if they cancel or not. So if the vectors do cancel, okay, it's going to be nonpolar. Like that. So if vectors cancel, we're going to have nonpolar. If they do not cancel, it's going to be polar. Okay, so what do I mean by if they cancel, if they don't? So I'm going to take these. So imagine picking this up, and we're going to put it right here so that we can add them together head to tail. So I'm going to draw that same arrow right there. Now you have to add them head to tail. So that means the tail of this one needs to be at the head of this one. So I'm going to pick that guy up and set him here. Now notice, these vectors aren't canceling. I have a dipole moment from the tail of this one all the way to the head of this one. So since they didn't cancel, I have a dipole moment, and this is a polar molecule. So dipole equals polar. So you can either look at the Lewis structure and say, hey, it has lone pairs, it's polar, or you can draw out these arrows, see that they don't cancel, that there is a dipole moment, and that it is polar. So I want to show you another one so you can see what nonpolar looks like using both sets of rules. So with carbon dioxide, we have, looking at the central atom, if I apply the Lewis structure way, are there any lone pairs on the central atom? No, so we're here with no lone pairs. But notice, there's also a no lone pair on the polar side. So now we need to look at the second half. If it's nonpolar, it's got no lone pairs, and the terminal atoms are the same. So are our terminal atoms the same? Yeah, they're both oxygen. So it's going to be nonpolar. Because over here, it's polar if there's no lone pairs, but the terminal atoms are not the same. So if this was nitrogen, which we've seen that case, then it would change it to polar. But since they're both oxygen, it is nonpolar according to those rules. Let's look at dipole moment. So oxygen, where's oxygen? So oxygen's more electronegative than carbon, so we're going to do the same thing. If I'm isolating this bond, we have an arrow pointing towards oxygen because it's more electronegative. We need to do the same thing to all bonds. This time they're going to cancel. They're in the same direction, or they're in the same size in opposite directions, not the same direction. So this arrow will cancel out this arrow, because if I try to draw them head to tail, they're going to be on top of each other, canceling each other out. So it would be impossible almost to draw them head to tail. It would look like this, and then they would cancel. Okay, so since they cancel each other out, there's no dipole, and it is still nonpolar, just like we said with these rules. So, which way do you prefer? Lewis structure way or the arrows?
Lewis structure.
Okay, so the reason I prefer the Lewis structure way as well is because when you start getting into 3D, like some of those with the wedges and the dashes, how do you draw the arrows there? Okay, that gets very complicated. So that's why I prefer that way, but it is your choice. I like to show both because some people do like that way. So I'm going to continue on and use this a little bit further. So we said water was polar, so you have that in your notes. We said CO2 was nonpolar, hopefully you have that in your notes as well. We're adding on to this even again. So actually I'll save those examples. We'll practice this a little bit more, and then we'll do solubility and melting point on Friday. Because that will take more than 15 minutes as described. All right, so let's throw up a few more examples. Not having any here. Okay. So, here's a few examples that we can classify as polar or nonpolar using our rules. The nice thing about this first one, before you start drawing it, is if you draw it, notice it's going to going to be a chain. We said if you have more than one carbon, the carbons like to form a chain. So it would be C, C, C in a chain if we started the Lewis structure of that guy. Right? And then we'd fill in the hydrogens around it. But you actually don't have to draw it. Because if you look at the rules, if carbon and hydrogen are the only atoms present, it's going to be nonpolar every time. It doesn't matter if I drew C20H56, okay? Still nonpolar. Doesn't matter how many carbons, how many hydrogens. However, if I toss in any other element, if I put an oxygen in there, or if I threw in a nitrogen, now I've made it polar. Okay, so it only applies if it's just carbon and hydrogen. This is often called hydrocarbons. You'll hear me use that word, hydrocarbons. That's when only hydrogen and carbon are present. These are organic molecules called hydrocarbons. So you don't even need to draw it when you get to something like this. Just look and see, hey, there's only carbon and hydrogen, so this is nonpolar. BH3, looking at this guy, you would have to draw it because we have no way of knowing just by looking at the element itself. And we actually drew this guy last time. He was an exception to the octet rule. Remember boron and aluminum in group 13 there? They were happy with just 6 electrons. They didn't need the full 8. Okay, that's one of those exceptions. So when we drew this, we have boron with the 3 hydrogens around it. Just like that. So when we drew it, boron had 2, 4, 6 electrons, and I was happy with that. We didn't have any extra electrons to throw on it. Excuse me. So, using this structure, this Lewis structure, is it nonpolar or polar?
Nonpolar. If the terminal atoms are the same.
It would be nonpolar, and the terminal atoms are the same. Because there is no lone pair on it, nothing there, but they're all hydrogens around it. So this would be nonpolar. What if I went and did something like this? Oops. So if I did this, it's boron again. That's the central atom because hydrogen can't be, right? So we'd have 1 hydrogen and 2 chlorines. It doesn't matter what order. I could have put the chlorine over there and the hydrogen down there. It's fine either way. If I drew the Lewis structure, there would be electrons around that. And now it's similar because there's no lone pair on the central atom, but it's now the terminal atoms are not the same. So by changing one of those hydrogens, or 2 of those hydrogens, I should say, out for chlorines, now we have 2 chlorines, 1 hydrogen. Terminal atom's not the same, so this guy would be polar. So I like to point this out because a lot of people will just say, oh, no lone pair is nonpolar. Look at the terminal atoms too. They matter. The terminal atoms have to be the same for them to be nonpolar, so those vectors can cancel that dipole moment. Because if they're not the same, the vectors don't cancel. That's the reason why the terminal atoms need to be the same. Before I do this one, I do want to talk about this last rule a little bit, because it's something that I don't think I talked about when we talked about the periodic table. So if you have your periodic table, you'll want to get it out. If you don't have a periodic table, you might want to get one from me. Let me try this somewhere. Yes, I do have my highlighted sheet. Good. Does anyone need a periodic table?
Can I have one that's not written on?
Yeah.
Thanks.
So, diatomic with the same 2 atoms. So, you're going to see this quite a bit. What diatomic means is 2 atoms together, right? So we have N2, O2, F2, CO2, Br2, I2, and then you also say H2. So, I have it highlighted on my sheet. Notice that there are 7 and that 6 of them make a number 7 on the periodic table. So if you start at nitrogen, oxygen, and then fluorine, all the halogens down through iodine. So all of those form diatomics in nature. What that means is you're never going to see an oxygen atom hanging out by itself. It's always going to be O2. Nitrogen, never just one nitrogen atom. It's unstable. So it's going to pair up with another nitrogen atom to make N2. Same for all the halogens. Now I said there's 7. Notice there's just 6 right here though. 1, 2, 3, 4, 5, 6. So hydrogen, who likes to hang out over here by himself, is included in those diatomics. So hydrogen, you'll never see just H. No, it's unstable that way. It pairs up with another hydrogen atom to form H2. That way it has 2 electrons, it's got the full shell for it, and it's happier that way, more stable. So if you ever see any of these, they're nonpolar, because you could even do the electronegativity subtraction between them. We've done one before. They both have the same electronegativity, so those electronegativities are going to cancel out, making it a nonpolar molecule. So I think you've seen an example of every one of these rules, at least. What we're going to do with these rules next time is apply them. So I'm going to give you a pair, an example of like maybe these two, or this one and this one, and I'm going to ask you, based off of just looking at those chemical formulas, which one has a higher melting point, are they soluble in one another. So we're going to look at properties and apply it to this nonpolar and polar concept. Okay, so that finishes out the chapter, is applying these to melting points and solubilities. So we'll do that on Friday. Anytime we have left, we'll start the review. Otherwise, Monday will be completely for review. So bring questions to me Monday, or email them to me if you're virtual, and I will answer them at the review on Monday. That's in there.